This is the way I've answered it. Okay. Helium is only single atoms, non-polar, very small, very weak London forces, very low melting points and boiling point. Right? Oxygen, diatomic, it's a bit bigger, relatively small molecule, still weak London forces, but a bit stronger than you got in helium. Then petrol, obviously, it's much bigger. And then this one, I haven't finished because I want you guys to finish it. It should basically be the same thing. It's a non-polar molecule with a 23 carbon chain. It's much bigger, therefore much stronger London forces.
So when you get a molecule so big that the London forces are as strong as the type of force, like a
yes. Yes. So what did I say? This stuff is a wax, right? C23H48 is a wax. Is a wax a solid or a liquid? Basically a solid, eh? So here the forces are getting strong enough to make this thing a solid. So how can such a weak force be so strong to make it a solid? So there's a few things that I want you to learn in my class. Right? I want you to learn the science, obviously, but there's some principles from science that move into other areas of life. And this is one of them. Small things are massively important, especially when there's lots of them. Okay? I learned this lesson once in my life, in a way I wasn't expecting. So when my kids were small, I was living in the UK, and they were at primary school, nursery school. So we go to their sports day. And they have a little sports day at this like nursery school / primary school thing. I don't know what school. I think it was primary school. But my boys were small and they're like these others. So now at some point in the sports day, they decide they're going to have a parents versus kids tug of war. So we're like, oh, all right, we'll mess about with him. So myself and about 5 other dads, get together, big rope, get the biggest rope, put him at the end. He's going to be the anchor. And all these little kids, a whole class of these little primary school kids get on the other side. We think we're just going to mess about with them for a little bit. What do you think happened? Honestly, we got slipped like we were being pulled by a tractor. I got the shock of my life. I mean, we're just going to, there's like 7, blokes, big bloke on the end. And we're like, okay, we're just going to mess with them a bit. And they start pulling, hang on, guys. We just got slipped. Well, firstly, you're in the UK, so it's wet. Okay, it's muddy. The floors, the grass, it's all wet and muddy, so there's not much traction. Secondly, how many feet have we got on the floor? There's 7 of us. 14 feet. How many feet have they got on the floor? There's 15 of them. They've got 30 feet on the floor. We've got more traction, we've got more friction. Yeah. They slipped us like we've been pulled by a tractor. How come? Small things are massively important, especially when there's lots of them. That's why you've heard people say, one day one of your teachers goes berserk and screams at somebody, you think, what the heck's the matter with them? But the thing is, this oak's been doing it every lesson for the last year, and the teacher's been ignoring him, and now today he does it, and it's like, can't handle it anymore. The small thing, one of your mates is like always laughing at you, poking you in the back or something. One day you just snap and you turn around and smack him in the mouth. What the heck? Yeah, but you've done it every day for the last year. And I've been ignoring it or telling you to stop, and you thought I was joking. I wasn't joking, I was serious. Small things are very important, especially where there's a lot of them. And you'll see this, intermolecular forces, even weak ones, can have massive effects. Right, can I move off there? Two bits of additional information I've given you so far this year that you need to pick up in addition to your science. One is, if you're talking nonsense and you're talking nonsense, it's fine. The other one is, small things are massively important. Okay. Sorry? What do you make? You made out of bonds. You're just one big chemical. You're just one big chemical. And when you do something, that's just one big reaction, chemical reaction. Right. Can I move on? Question is, have you got a free will? That's
C23H48.
it's
Wax.
probably a wax. I may not have got the formula exactly right, but when you get to that length of carbon chains, the molecules become waxy, become solid.
So what are the like properties of that?
So wax. So it's solid, but it's quite soft because it's not extremely hard. It's got a relatively low melting point. All the hydrocarbons will burn. So any hydrocarbon will burn. So that's why wax can burn.
So isn't that hydrogen bonding essentially strong?
What is the criteria you need for hydrogen bonding? Is there oxygen, nitrogen, or fluorine in it? So hydrogen in a molecule doesn't mean there's hydrogen bonding.
Make wax to a gas.
Yes.
You inhale the gas. Or like coat your inside the one.
Yeah. Right, can I move on? Cool. So this was just about dissolving. I showed you this before. I just made this slide to make, if you've got sodium chloride and it's going to be dissolved in water, there's a water molecule. The water molecule's got a negative bit and a positive bit and a negative bit because of the electronegativity differences. Because of that, I show the water molecule as a dipole. This here represents a water molecule. The red bit is the positive bit, the blue bit is the negative bit. And it would arrange itself with its negative bits attached to the positive sodium. But there wouldn't just be one, there'd be hundreds of them. And around the chlorines, the positive bits would be attracted. Now, what happens when it dissolves? What happens is this. When those things gather like that, they look like this. Negatives attracted to the positive, positives attracted to the negative, and then they pull it apart. Watch. See? They pull it apart. When you stir the liquid, the water molecules gather around, they rip it apart. Now, it took me to make that animation. All right, so that's just explaining how solvent molecules can pull apart the solid molecules of something that you throw into it. If the forces are similar, so dipole forces and ionic forces similar, so they'll dissolve. Because the forces are similar, they can substitute for each other. And the forces between water and salt would be ion dipole forces. Because the water is a dipole and the table salt gives you the ion. All right.
Can you explain why the things in the molecules pull apart again?
So here, what's happened is the negative parts of the water molecules are all attracted to the positive sodium ion. The positive part of other water molecules are attracted to the negative chloride ion. And now you must remember, over here, there's going to be other water molecules, and the positive part of those water molecules will attract to the negative part of these water molecules. So you've got like a whole chain of water molecules here. And because there's so many of them, they just rip it apart. So as soon as you stir it, the water molecules move around and they just pull it apart. Happy? So in water and table salt, you've got ion dipole forces. Now, what have you got in a molecular solid? Right, so what's a molecular solid? It's a solid that's made up of molecules. So you get ionic solids that are made up of ions. You get molecular solids that are made of molecules. You also get other types of solids. We'll talk about them later. A good example of a molecular solid is iodine. Why? Because it's made of I2 molecules. What's an I2 molecule? It's two iodine atoms strongly bonded together with what kind of a bond? Covalent bond. Pure or polar? Pure. So in between those two iodine atoms, you've got a pure covalent bond. Strong covalent bond. See there? Between the two iodine atoms. But what bonds have you got between the two iodine molecules? London forces. And are London forces strong or weak? So between the molecules, you've now got very weak London forces, weak intermolecular bonds. That means these solids have got very interesting, well, unique properties. They've got low melting points. They're brittle. They're soluble in non-polar solvents. They don't conduct electricity. All of those properties you can get from their bonding. Okay? The melting points are low because the bonds are weak. Yes. They're brittle because the bonds are weak. If you smack it, it's going to fall apart. They're soluble in non-polar solvents. Why? Because they're non-polar. The solvent's non-polar. Forces are similar. They can substitute for each other. Why are they non-conducting? You will take it in. And now I'm going to have to watch you. Playing chess online during science. So your computer has to be closed in future. If that happens again, I'm going to ask for a meeting with your master. So gentlemen, you must not only be able to identify the different types of bonding in the molecules, you must also now start to be able to figure out the properties of the substance based on bonding. Why is it non-conducting? What do you need in order to be able to conduct electricity? Electrons? Well, they've got plenty of electrons. I mean, each iodine atom's got 53 electrons. There's plenty of electrons there. They have to be moving around. Well, they have to move around to make an electric current. Now, can you get can those electrons move? Why not?
No,
where are they? They're held in the covalent bond. Right? Those electrons are held tightly in the covalent bond. They're not free to move around. Are there any ions in there that can conduct electricity? No. So there's no ions, there's no free moving electrons, non-conductors.
So any pure covalence won't.
Any pure covalent substance won't conduct electricity. So that's theoretical chemistry. See, 2 weeks ago you were a theoretical chemist, now playing chess. Right, so we've done this thing a few times. Here, all I've done is I've done that in a lot of detail. Now you don't need all that detail. But if you want it, you can photograph it if you want to. I'm not going to make you type it all out. We've explained it. We've been through it a couple of times. I'll put it up on Teams. Right? But it's just explaining the solubilities based on the intermolecular forces. All right. Now, I need to run out of time in 2 minutes. Your folks have paid for these 2 minutes, guys. Can't shortchange them. Okay, let's talk about vapor pressure. What the heck is vapor pressure? If you've got a liquid, these two contain little windows here are supposed to be snapshots of what's happening at the surface of a liquid. The liquid on the left and the liquid on the right, they look the same, but what do you notice about the space above them?
Less crowded on the left.
It's less crowded on the left. Okay, so what happens is any liquid that you've got, some of the particles in the liquid have got more energy than others. They never all got the same amount of energy. It's like you guys. Some of you got a lot of energy, some of you got a little bit. Some of them have got enough energy to escape the liquid and go into the vapor phase. So any liquid would have a little bit of its vapor above it. And if you block this thing, that vapor would eventually get saturated and then some of it would go back down. Now, tell me, if you think, if the forces in the liquid are strong, would you have more vapor or less? If the forces in the liquid between the particles are strong, Would you have more vapor or less? Less, you agree with? So which one of these two do you think has got the strongest intermolecular forces? The one on the left. Now, in order to boil something, what do you have to do? You've got to give it enough heat so that you break the forces in the liquid so they can all go into vapor phase. So if it's got stronger forces, are you going to have to heat it more or less? More. So which one of those do you think is going to have the higher boiling point? One on the left. Because you need more energy to break those bonds. So look here. The vapor pressure is the equilibrium pressure of the vapor above the liquid, right? And what it means is this. This one has got a low vapor pressure because there's hardly any vapor there. This one's got a high vapor pressure. The one with a higher vapor pressure is easier to boil. So here you've got weak intermolecular forces and a lower boiling point. Here you've got strong intermolecular forces and a high boiling point. And then we're done.